Jessica is a lifelong space enthusiast with over a decade of professional marketing and communication experience. Her fascination, appreciation, and enthusiasm for space spans entertainment, art, literature, and fashion, and was ignited when, as a child, she was encouraged to consider the consequences of whether we are alone in the universe or not. She is committed to continuing the conversation about space exploration with her neighbors and her community, and dedicated to inspiring the next generation of scientists, engineers, and explorers. Jessica joined the NASA Solar System Ambassador Program in 2021. She will present an overview and update of the Nancy Grace Roman Space Telescope. And she just recently moved to Grass Valley, so we're very happy.
And she joined the club tonight.
And, well, that's up to her, but hopefully she will join the club.
No, we already did.
Oh, you did? Oh, hey, there you go. So we're happy to have her. So let's welcome Jessica.
Hi, everyone. Thank you for inviting me to present tonight, and give a little spoiler, but I believe I'm the newest member of the club, and my husband Kyle, who's in the back. So tonight I'm presenting Expanding Our View, the Roman Space Telescope. And as we already said, my name is Jessica, and I'm a Solar System Ambassador. So what is a Solar System Ambassador? So this is NASA and the Jet Propulsion Laboratory, or the JPL. They manage this program, which works with volunteers across the country who hold events to share the latest science and discoveries from NASA space exploration missions. Not that different than what all of you do as volunteers, and from what I'm learning about your work. I'm going to go a little bit off script and share a story. One of the reasons that I'm standing here today presenting to this club is because when I lived in San Diego, I saw a sign on the side of the road that said "Star Party" with an arrow. And some friends and I were, well, let's go see what that is. And it turned out to be the San Diego Astronomy Association. And I spent years working with them. And they taught me so much about anything that I know now and about the sky. I partnered with them for many events. And after I became a Solar System Ambassador, I had the honor of being the guest speaker at one of their annual meetings. So clubs like this are really, really important to me. So thank you so much for having me tonight. I know that when some of you hear NASA, it might conjure images of astronauts and scientists and engineers. I am none of those things. I am a marketer, and I currently work for the state of California in education and outreach. But I'm just somebody who's always had an interest in astronomy and was introduced to it by just some amazing volunteers. And so this is my 6th year as an ambassador. And while I don't have the expertise to lead a highly scientific discussion about spacecraft builds or instruments, which I hope you will all remember that at the end of the presentation when we do questions. I do plan on sparking, even you already have this spark, but I do want to just share the spark of curiosity with all of you about our universe and the excitement for the future of space exploration. So it should be about 40 minutes, I think, that I'll be up here. And if you can hold your questions, I'll be around afterward. And you'll see me at other events because I'm a member now. And so with that, I am honored to share my excitement about the Nancy Grace Roman Space Telescope. So raise your hand if you're already familiar. Oh, this is going to be great. Oh my gosh. You're all going to walk away with your brains melted. So Roman is a NASA observatory, which is designed to unravel the secrets of dark energy and dark matter, search for and image exoplanets, which are planets orbiting a star other than our sun, and explore many topics in infrared astrophysics. NASA missions are often named for pioneers and trailblazers in science. Nancy Grace Roman accepted a job at NASA in 1959, just 6 months after the agency was formed. Dr. Roman was the first female executive at NASA and the first chief of astronomy. She worked diligently to plan for a robust suite of satellites and rockets to be managed by NASA, including space-based observatories. She advanced space-based astronomy and general astrophysics knowledge, and the telescope bearing her name will take up that legacy by addressing big questions crucial to the future of the field.
What are dark matter and dark energy? How common are planetary arrangements like our own? And how many planets in our galaxy have the potential to harbor life? The Nancy Grace Roman Space Telescope will help answer these fundamental questions. Each image from its wide-field instrument will have the depth and clarity of Hubble's best, but capture a sky area 100 times larger. The Roman Space Telescope will take the lead in exploring dark energy and dark matter. We only know they exist by their effects on observable matter, yet these two mysterious components make up 95% of the universe. The Roman Space Telescope's powerful 2.4-meter mirror and enormous field of view will also help us in the search for planets beyond our solar system, or exoplanets. To deepen its study of exoplanets, the Roman Space Telescope will house a beyond state-of-the-art coronagraph that will directly image and analyze Neptune-sized planets in orbits slightly larger than Earth's, a dramatic improvement over current capabilities. The Nancy Grace Roman Space Telescope will help us answer many of the biggest cosmic questions. Roman will be an indispensable part of space science during the next decade and beyond.
So that is a lot to unpack. So let's go over some of that together. We'll start with the mission overview. So Roman is set to launch from NASA's Kennedy Space Center in Florida no later than May of 2027, but more on that later. The mission lifetime is expected to be 5 years, but there is potential for that to extend. Roman will operate on an orbit around the second Lagrange point of the Sun-Earth system. So Lagrange points are basically just positions in space where objects tend to stay put. The telescope will be a cutting-edge space observatory for in-depth studies of the universe in infrared light. It's a survey mission, meaning it looks broadly rather than focusing on a selected target. The telescope's large field of view, high sensitivity, and advanced coronagraphic capabilities will allow astronomers to detect and study galaxies in the very early universe, search for potentially habitable exoplanets, and provide answers to some of the most pressing questions in astrophysics, such as the nature of dark matter and dark energy. Before we get into the instruments and science of Roman, let's reflect on how we got here. Since the first astronomers pointed telescopes at the heavens, they have sought to see more, to see farther, and to see deeper. The 20th century of astronomy tackled and solved many questions, but the pursuit of distant objects and galaxies helped drive even larger and more capable facilities, including NASA's Great Observatories program. This program included a family of space-based observatories, each observing the universe in a different kind of light. The Hubble Space Telescope was the first of the program, and arguably the best known. Hubble launched in 1990, and several servicing missions added additional capabilities to the observatory. The Spitzer Space Telescope was launched in 2003, and it was the last of the program. So how did NASA's Great Observatories program shape our modern space telescopes? Every discovery in astronomy leads to new, exciting questions and new, exciting missions. Each mission leads to the innovations of the next mission. Hubble and Spitzer's infrared capabilities sparked a desire to see more infrared light at a high quality, and the Webb Space Telescope mission was born. Discovery of dark energy with Hubble led to Roman being named the top priority major space-based mission in 2010. All of these missions are complementary and they work together. Areas where the telescopes overlap on wavelength sensitivity allow them to support and follow up on each other's observations. Data collected by astrophysics missions are archived and available for future astronomers to reference, compare, and contrast with new observations. So observations taken by Roman in 2030 could be compared with Hubble's observations from 1995, and discoveries could be made using both the new and archived data. Roman's broad view may discover unique objects that Hubble and Webb can then target to study in greater detail. Compared to Hubble's infrared capability, Roman is 200 times the infrared field of view, with the same high quality and high resolution data. This image of the Eagle Nebula compares Roman's large field of view with Hubble's famous image of the 3 dust pillars shown at the center. Each outlined area shows the telescope's field of view and what they capture in a single shot. Webb has the sensitivity and wavelength range to capture detailed images deeper into the universe than ever before. Roman's wide field of view will rapidly survey huge areas of sky while still rivaling Hubble and Webb's resolving power. Webb will tell us about the early universe, and Roman will help us understand the bigger picture of how the universe works. This could be what astronomers need to finally make progress on the mysteries of dark energy and the nature of dark matter that have been difficult to solve. To understand how Roman will do that, we're going to take a short tour of its main systems.
NASA's Nancy Grace Roman Space Telescope is designed to answer big questions about the universe. What is dark energy, which seems to be speeding up the expansion of the universe? How many planets exist among the stars, and what are they like? The Roman Space Telescope is similar to Hubble, but benefits from 30 years of technological development. It will view the sky on a scale never before accomplished from space. This is where Roman is closest to Hubble. It has the same size and type of main mirror, a 2.4-meter precisely shaped piece of silver-coated glass. The size of this mirror is partly how Roman matches Hubble's resolution. Roman's main camera is the wide field instrument, which will take infrared pictures of the sky to study dark energy, observe galaxies and stars, and find exoplanets. Instead of Hubble's single first-generation image sensor, the WFI incorporates 18 third-generation chips that allow it to take pictures capturing 100 times greater sky area than Hubble's. Each 300-megapixel image will enable scientists to study a large portion of the sky. At Roman's back is its primary means of communication with Earth, the high-gain antenna. This antenna will be responsible for sending nearly 1.4 terabytes of data to ground stations every day. That's the equivalent of 460 hours of streaming video. Roman's critical systems, such as power and data handling, are located in 6 modules at the spacecraft's rear. These include 6 rotating reaction wheels that control where the spacecraft points, nearly 1 ton of propellant for larger movements, and a 10-terabyte data recorder. Roman's other instrument is its coronagraph technology demonstration. A coronagraph blocks a star's light to capture the faint light from orbiting planets. It will be the first time a space telescope has used deformable mirrors to precisely control the incoming light, and special masks to block only the starlight. This method will enable Roman to capture direct images of distant planets and even analyze the light that is reflected off their surfaces, allowing scientists to learn about their composition and atmospheres. The spacecraft's solar panels provide its power by converting sunlight into electricity. They also shade the spacecraft, helping to keep its instruments at their design temperatures. The solar panels will be able to provide 4,100 watts of power, enough to run 2 commercial microwave ovens. With all these systems working together and in partnership with powerful future telescopes, the Nancy Grace Roman Space Telescope will be able to usher in a new era of studying our universe.
So it's pretty amazing. So let's take another look at 2 of Roman's instruments. The Wide Field Instrument, which is Roman's primary science instrument, and the coronagraph, which is its technology demonstration instrument. The wide field instrument is designed for those survey-style observations. It is a camera made of 18 individual detectors and provides that field of view that is about 100 times that of Hubble's survey camera. And as I mentioned before, about 200 times that of its wide field camera.
The Wide Field Instrument is the heart of the Nancy Grace Roman Space Telescope. It is what allows the Roman Space Telescope to take pictures with the same detail as Hubble, but covering an area 100 times larger. Despite this incredible power, the basic design is the same as telescopes around the world. Light enters through Roman's 2.4-meter aperture and is reflected and focused by the curved main mirror, which is also the largest mirror in the telescope. This light is reflected and focused once more by the secondary mirror. More elements tighten the beam and strip it of stray light rays before it passes through the filter wheel. This wheel has a variety of filters that allow different wavelengths of light to pass through. It spins from one to another depending on what the researcher is looking for. Finally, the focused and filtered light reaches the focal plane, where it creates an image on the detectors. These detectors use the photoelectric effect to convert photons into an electrical signal that is then decoded into an image. In Roman's case, there are 18 detectors, allowing it to create 300 million pixel images of large patches of the sky. The large number of detectors and pixels gives Roman its wide field of view. The size of the mirror and the precision of its optics gives Roman its fine imaging. This combination of image size and detail has never been possible on a space-based telescope before, and will make the Nancy Grace Roman Space Telescope an indispensable tool in the future.
And while Roman's coronagraph instrument is not the first coronagraph in space, it will be the first high-performance coronagraph system on board a space-based observatory capable of direct imaging of exoplanet systems. It will inform future potential NASA missions aimed at imaging and characterizing Earth-like planets orbiting nearby stars.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. The Nancy Grace Roman Space Telescope's coronagraph doesn't block the star's light with an opaque disk, as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own.
So all the details about Roman that have already been discussed are designed for making scientific breakthroughs and answering big scientific questions. Some of these questions arose after discoveries by other missions, but others are as old as stargazing itself. How did we get here? How does the universe work? Is Earth the only home to life? Roman will allow astronomers to explore the full range of the cosmos and observe planets by the thousands, stars by the billions, and galaxies by the millions. So we've talked about exoplanets, which is how astronomers distinguish between planets in our solar system and those that orbit other stars. Roman will study both planets in our solar system and exoplanets. The first exoplanets were discovered in the 1990s. Since then, more than 6,000 exoplanets have been confirmed, and scientists now estimate that most stars have at least one planet orbiting them. This means that there are countless other solar systems waiting to be discovered. About 100 known exoplanets were discovered using microlensing with ground-based telescopes. Microlensing studies the way planets that are between a star and a telescope distort light from the star. By studying the distorted light, astronomers can determine a planet's properties, like size and mass. Roman will take this technique into space and use it to discover small, rocky exoplanets that are harder to detect using other methods. Combined with results from other planet detecting missions, Roman will provide a much fuller census of exoplanets and a better understanding of how unique or not our home planet and solar system are in the universe. Roman will also help shed light on the solar system's history and development over time. Its systems and observations will enable discoveries of objects in the solar system that have previously gone unseen, because as Roman looks into distant space, it will also be capturing a lot of information about the solar system in the foreground. This means that we'll get a wealth of data both on known solar system objects, 8 planets, dwarf planets, moons, asteroids, plus new, previously unknown, small, faint objects. Astronomy began with stargazing. There is still so much we don't know about how stars form, how they affect one another in dense star-forming regions, and the role they play in the development of galaxies over time. A combination of 3 things makes Roman's study of stars special. Roman will detect near-infrared light, which passes through cloudy nebula to reveal stars hidden in visible light. Roman's high resolution will provide unprecedentedly clear views, and Roman's huge field of view will collect a census of stars that will provide new insight into their still mysterious formation and processes. Stars are engines of creation, fusing elements that go on to make up the rest of the universe, including elements like carbon, oxygen, and nitrogen that are essential for life on Earth. This is why discovering the secrets of star formation and development are important to understanding overall big questions about the universe and life as we know it. With Roman's near-infrared capabilities, Roman can see through some of the obscuring dust to study forming stars embedded inside. With the large expansive view, Roman can study how star formation in one region can affect star formation in other areas of the same nebula. It could limit it or it could encourage it. We'll be able to view various stages of the stellar life cycle in one environment, including young protostars blasting out jets, star clusters, clouds of gas and dust, and stellar death when it has expended all of its fuel. And for massive stars, this is a supernova. This image is a very small fraction of Roman's field of view. There are so many stars at the center of our galaxy that in other telescopes' views, they blur together. But Roman will see them with high clarity, distinguishing stars in the center bulge from those in the surrounding disk. Roman will pinpoint precise locations for over 200 million stars in the bulge, allowing for study of their movement over time, and with that, the history of the Milky Way's star formation. The galaxy shown on this slide is our Milky Way's closest large galaxy neighbor, the Andromeda Galaxy. Galaxies are huge cities of stars, and nearby galaxies are an opportunity to study how stars interact and behave on this large scale. Roman will give us a sharp new view of nearby galaxies. Rather than a blur of light, astronomers will be able to count the individual stars of those galaxies, like giant, or like grains of sand on a beach. What is the relationship of individual stars to the whole? Stars are individual puzzle pieces that make up the whole picture of a galaxy. Understanding of individual stars and regions of stars in a galaxy provides a better understanding of the entire galaxy. How is it similar to our Milky Way galaxy, and how is it different? By building up a library of galaxies over space and time, scientists can study patterns in the history of galaxy development over time, formation, mergers, and growth. The volume of galaxy data will also allow scientists to study the history of the universe and the mysterious phenomena of dark energy as it expanded the space between galaxies. By using Roman to survey the entire surrounding environment of nearby galaxies in different colors with accurate positions, astronomers can look at individual stars and satellite galaxies and the galaxy halos or outskirts to understand the history of merging that created the galaxies seen today. Essentially, Roman's field of view will enable astronomers to map out nearby galaxies and their surrounding environment and provide insight into how neighboring galaxies interact with each other. Roman will find a diversity of galaxies at different stages of their evolution. Galaxies in small groups and in large clusters, merging galaxies, and newborn galaxies. By capturing both volume and detail, Roman will advance knowledge about galaxies and their variety of forms, and also their evolution over the history of the universe to help us understand how the galaxies work, including their central supermassive black hole activity. Roman will observe galaxies back to when the universe was just a few 100 million years old, substantially increasing our sample from this very distant past. Roman will capture up to 1 million galaxies in one dot. We've observed just a handful of distant galaxies, but Roman's observations will include thousands of galaxies in the very distant universe. This will enable better estimates of how quickly star formation was occurring in young galaxies of different masses, which affects how quickly heavier elements were formed in the early universe. seeing this big picture of the universe with Roman will shed light on big mysteries in astrophysics, where currently it is dark. There has only been a trickle of data from current telescopes. It is possible that a big part of the reason dark matter and dark energy are still so mysterious is that we just don't have enough information to figure them out. We can't solve the cosmic mysteries with a trickle. We need an enormous amount of data to understand the nature of dark energy and dark matter. Everything that has been observed in the history of astronomy makes up only 5% of the content of the universe. There is so much more to discover. It is possible that the solutions to some of these mysteries concern new laws of physics that we are not yet aware of, beyond the current theories of Newton and Einstein. The universe is so large that if we ever want to get a glimpse of how the universe changes over time, we need to look far back into the past, which means looking at objects far away. And we need to capture a lot of the sky too. Past deep surveys have been pencil beams in the sky compared to what Roman will capture. The changing rate of the universe's expansion is a huge question astronomers are trying to answer, driven by the phenomena that we call dark energy. This means that there is likely an important piece of the puzzle that is missing from our understanding of the laws of physics. Astronomers use type 1a supernova to measure the universe's expansion rate, but they're uncommon. So we need to search the skies often enough to get a chance to find them. Roman will play the numbers game here by observing a big patch of sky over and over again, upping the odds of finding these rare objects. Then Roman can track the expansion history of the universe farther back in time than we have been able to so far. Dark matter cannot be directly observed by telescopes, but its mass warps space and acts as a gravitational lens, redirecting light that passes by it. And these gravitational effects can be seen. Uncovering the mysteries about dark matter will require mapping out the curved paths of light and backtracking to figure out the distribution of dark matter to cause the gravitational lensing. Dark matter can also cause the shape of galaxies to be warped, which requires the high precision imaging that only Roman can provide for a very large number of very distant galaxies. Roman will investigate all the scientific questions we've discovered and provide so much more detail. But it's the discoveries we can't anticipate that are some of the most exciting. Dark energy was like this for Hubble. No one saw it coming. And now it's a large focus of research and future missions, like Roman. With its clarity and repeated observations of the sky, Roman will inevitably find unique objects. Survey missions like Roman are ideal for observing changes in the dynamic universe. How has it changed over time? To quote Nancy Grace Roman, scientific research and engineering is a continuous series of solving puzzles. Even when Roman is studying distant galaxies, it will capture a wealth of data on intervening solar system objects, stars, star-forming regions, and nearby galaxies. Many areas will be repeatedly covered, providing detailed observations of transient objects, many of which are sure to surprise astronomers. Roman will survey an area in near-infrared light in less than half an hour, whereas Hubble took nearly 21 days to survey a similar area. All of this data will immediately be available for free within NASA's archive and accessible by anyone with an internet connection. Many of the biggest questions in astronomy require information about numerous objects at different times in cosmic history. As I said, all of Roman's data will be non-proprietary and available to all. The Roman mission will also partner with the astronomical community to create and release open source data reduction and analysis tools. Roman will complement future ground-based missions of the more nearby universe, which covers more of the sky. It will scout the universe for unique objects that can be followed up on by more targeted telescopes. We learn the most about the universe when we can study it at many different wavelengths, in different parts of the sky, and at different eras in the universe. Future astronomers will be able to look back on Roman's data to see what the universe looked like when Roman was observing it. Roman will capture and reveal the big picture, and maybe, just maybe, it will help answer some of our biggest questions. How does the universe work? How did we get here? Are we alone? In closing, I'd like to share one final video, which opened the press conference that NASA held last month about the Roman telescope.
We have a standard model that is exquisite at describing the properties of the universe that we live in. But there are hints of a problem with that model. Roman will tell us if our model is wrong.
Andrew, are you ready to go?
You're good? We're ready.
And what's spectacular about Roman is Roman will be able to tell us if we were wrong and put us on the path to figuring out what's right.
Starting run.
This time, a year from today, we're going to have a different understanding of the universe than we have right now because of the observations from the Nancy Grace Roman Space Telescope.
Control reports, test complete.
So in the beginning of this presentation, I noted that the mission is slated to launch no later than May of 2027, and I am happy to say that NASA has confirmed that we are go for launch ahead of that commitment. NASA announced the new timeline during a news conference on April 21st, which is available on NASA's YouTube channel if anybody would like to watch that. So I hope that you'll check that out and stay tuned for all that Roman will discover when it launches. Its target is September of 2026. And so thank you all for going on this journey with me. We certainly covered a lot of information today, but we've really barely tapped into how much information is out there about Roman, its science, its instruments, and more. So if you want to learn more about Roman's build or instruments and keep up with the latest news, explore interactive features, access loads of free content, artwork, and activities, which would be great for outreach events. A lot of that is free on NASA's website. If you have any questions that can't be answered on the NASA website, you can find me on the NASA Solar System page and message me with your questions. If you're here in person, I think I have a couple of business cards as well. And I can do my best to reach out to my coordinator and try to find those answers for you. So thank you again for having me tonight.
Thank you.
I have a question. Where is this being built? We had a lecture on James Webb, I think, a couple of years ago. I think that was in South America, in Guyana. Weren't they assembling it there?
So,
Where is this? Are components coming from different countries, or is it all in one place?
yeah, I used to do a web, well, not used to, but I have a web presentation where I would talk more about the build. This, I believe a lot of this was built at the Goddard site. So here in the United States.
So that's in Florida, right?
Mm,
Where's Goddard?
I don't remember where that one is.
Do we know where that
Does
is?
anyone know?
DC. Maryland. Where? Maryland. Okay.
I believe, but we can confirm that, yeah. And I'm sure as there often is, they work with many other like commercial agencies to get all of the parts. But I believe that they built and tested it
It looked like the process is similar with
web, like,
you
yeah.
know, all this
Clean room.
plastic.
Yeah, I wouldn't want to be the person who has to clean that mirror. That's, yeah.
Question. Since you mentioned that Roman has about a 5-year mission, is there anything on the planning sequence now for its follow-on?
I'm not aware of another space-based telescope. I mean, Webb is still out there, but I don't know what comes next. I think maybe we'll see what we discover with Webb and Roman.
Thank you.
It's going to the same place that Webb is at, right? It's going to L2.
The L2, yeah.
Right,
Mhm.
so, you know, they had an elaborate canopy to protect it from the sun. I'm just wondering and the heat. I was just wondering what the story was with Roman.
How Roman is it have it?
Yeah.
So
It looks
I
like it's
think
all
it's,
in one. It looks like it's in like one piece.
yeah, if I remember correctly, a lot of the build of Webb, they had to protect the certain like elements, so maybe it's the way that the
That's because
spacecraft
of the
is
low
built.
temperature too. right?
Yeah,
That's part of it.
yeah. I haven't come across that in my research of Roman, big on the build of them. Obviously, this doesn't have the shield that Webb,
Yeah, that's great.
the same shield that Webb had.
Yeah, one over there.
If anyone's, I can't see because of this light, so you guys just
There's
shout.
one over there.
Question over here.
Wonderful.
Hi. The camera, the 18 sensors have gaps in between them. Is that intentional, unavoidable?
Yeah, that sounds like a real technical,
That's my take.
so we could look that up. So
Okay.
we could, yeah, so I have, I was not able to grab them because we just moved and so everything's in boxes and I don't know where it is, but since I'm a member now, next time I come to an event, I have some printouts of some different one-sheeters with more information, and there is one that goes into depth about the camera, I believe.
Thanks. I do some imaging, and
Oh.
by luck, whatever I'm imaging will be right between the sensors, there's little gaps there.
So it looks like there's one primary mirror, right? It's in the web, it's sort of folded out and it's
Mhm.
larger. But it sounds like it's an electronic method in order to get such a wide field, is that right? Because it can't collect as much light, as much infrared information as web, but it must, it must be like whatever is receiving all the information has got to have more receptors. I don't know, guys, what do you think? It has such a wide
Technical
field.
people.
It's my first day.
Yeah, Webb was right, a
Remember after
massive.
after it folded?
Yeah, they had to come up with brand new ways to get. Is everyone familiar with the James Webb Space Telescope? So Webb, so whereas the Roman Space Telescope is expanding our view, the Webb Telescope was unfolding the universe because they had to come up with a new way to launch it because the mirror was so large. It had to fold in like origami style in order to get into space, and they had to unfold it. And Webb is imaging items or objects where like Roman would survey a larger area, and then you can point Webb at something that
There's
looks
deeper in
interesting.
space, I think, it's more
Yeah,
concentrated.
yeah.
And maybe that's why it needs the shield, because it's so big, I don't know. Because look like
Yeah.
this one's contained in like a big can or something.
Field of view is very dependent on the focal length.
Okay, so you think this one has a wider focal length?
Shorter.
Shorter, I mean, shorter focal length, right? Flatter mirror.
And I think based on the previous diagram, Webb goes deeper into the infrared too,
Yeah.
right? So it needs more cooling essentially to get down
Right,
there.
okay, yeah, that
Yeah.
makes sense.
Is ever gonna watch the launch? Yes, I saw some heads shake, so good, good.
So when is it scheduled?
Well, they're targeting early September, but they haven't released,
They don't have
A
an
window
exact date
yet.
So
Yeah,
we'll,
not
I
yet.
guess we'll hear.
yeah, yeah.
Well, you'll tell
What
us,
is it
right?
launching on?
You'll tell us on Groups IO.
Okay.
I'm really bad at this question, it's like,
I think it's
yes,
Falcon,
yeah, it's like the one that they all launch on, I can never remember. Heavy Falcon, yeah, yeah. I'm bad at that part. What I'll probably do is as launch gets closer is I'll develop additional materials that talk a little bit more about some of those details. Whereas we just found out that it's fully built and ready to launch, so I was still doing a lot of just, hey, get hyped about the mission. But now we've got to get some information together about the launch, which will be really exciting.
Yeah, it looked like in the last photo, it looks like it was all in the capsule, it was in the capsule and ready to go, right?
In the video,
Yeah, the video, I think.
yeah, it's fully built. Yeah, it's completely assembled and tested, and yeah. If you watch the press conference, which is on their YouTube channel, I believe the NASA administrator and some of the leads from it are sitting, and behind them is Roman, fully assembled.
They don't happen to have a backup, do they?
No, this is not the Voyager mission where they launched twins. There's just one, so everybody just cross your fingers. But we've had some great successes recently. I was when Artemis recently was successful, I thought, gosh, sometimes we take for granted because we've seen Webb launch successfully and the Artemis missions have been successful that we forget like a billion things that could go wrong and just crumble, So it's incredible the work that's done. I remember when I was presenting about Webb, I don't remember the numbers now, but I had a slide that showed like all the countries that it took, all the people, right? Scientists and not just scientists, but just all the people it took to launch this. And we forget about that because we see a shiny telescope returning amazing photos that, maybe not this group. This group probably thinks a little bit more about some of the work. But there was another question, I think.
Yeah, wasn't it almost canceled?
Roman?
Yes.
So I don't think Roman was ever at risk. There was obviously some, budget stuff, but Roman was so far along. I will say they're not only ahead of schedule, they're under budget. So if you watch a press conference, they say that like 8 times. But I don't think it was ever actually at risk. I think there was a lot of things that people weren't sure about at one point recently. But Roman had already progressed so far, like by the time those conversations were happening, it was already very far along and had even completed some testing. Unless there's something before the build that I'm not aware of.
So had the wind farms.
Yes.
They progressed very far.
Are there major subcontractors that have put together like, certain aerospace firms that contributed certain parts of it? I imagine this,
Yeah, there always is, like Lockheed Martin and some other ones are always, I feel like always part of it. I don't have that specific information in this presentation, but I'm sure they have the information on the website, where they talk about who contributed, what. And as I said, I'll develop like additional ones about how this all came together. And maybe I'll come back and do another one.
Do you know who built the mirror?
No, we could probably find that pretty easily though if we popped onto the website is going to have all the information about all that like highly technical stuff. There's probably some press kits as well.
Not the same one that developed the mirror for public, right?
But according to Bill, they made multiple mirrors, right? They picked the wrong one.
Yeah.
Yeah. The good ones in Smithsonian. The good ones in the Smithsonian.
Well, thank you
Well, good.
so much, everyone.
Thank you.